Tonight, something is passing between you and the moon, right now, and the scientists tracking it cannot tell you how big it is, not approximately, not roughly. The field in the database where the diameter should be is completely, perfectly blank. The asteroid has a name, 2026 EG1. It has a speed, 21,500 miles per hour. It has a trajectory calculated to the minute. What it does not have is a size, and it is not alone. 9 asteroids in 1 week, not one of them physically measured, and a solar storm arriving the same night. Stay with me until the end of this video, because what that blank field actually means for planetary defense will genuinely change how you look at the night sky. If this has you hooked, subscribe to the Skylab, because asteroid discovery is outpacing characterization, and we'll be here reporting on all of it. Drop a comment telling me where you're watching from, and tell me honestly, do you think 9 uncharacterized asteroids passing Earth in a single week is just normal solar system background noise? Or is this the planetary defense gap revealing itself in real time? Now let's get into it. Part 1. The 1-hour countdown. Right now, as you're watching this, an asteroid is closing in on Earth, and nobody can tell you how big it is. Not an estimate, not a range, not even a rough guess scrawled on a whiteboard somewhere at a NASA facility. The fields in the public database where the diameter should be listed are completely, perfectly blank. And in less than an hour from the moment this video goes live, that asteroid will reach its closest point to our planet, 318,000 kilometers away, sliding between Earth and the Moon like something that was never supposed to be noticed. Its name is 2026 EG1, discovered just days ago. Travelling at approximately 9.6 kilometers per second relative to Earth, that is around 21,500 miles per hour. Its closest approach is scheduled for 0327 Coordinated Universal Time on March 13th, 2026. These numbers are not estimates. The orbital mechanics are extremely well established. Scientists know exactly where this rock will be, to the minute, with extraordinary precision, and yet they cannot tell you what it looks like. They cannot tell you whether it is the size of a house, a stadium, or something considerably larger. That combination, perfect positional knowledge paired with zero physical knowledge, is not a contradiction. It is actually a window into how planetary defense really works, and more importantly, how it sometimes does not. Let us put the distance in perspective, because 318,000 kilometers sounds like a lot, until you remember that the Moon sits at an average of 384,400 kilometers from Earth. That means 2026 EG1 is passing closer to us than the Moon is right now. It will cross inside the Moon's orbital distance. Astronomers call this a sub-lunar flyby, and while hundreds of them happen every year, most involve tiny objects, rocks a few meters wide that would vaporize harmlessly in the upper atmosphere if they ever wandered too close. The problem is that without a size measurement, you cannot confirm which category a new object belongs to. You're working blind, statistically. You know the probability of it being small is high, but probability is not the same as certainty, and certainty is exactly what planetary defense is supposed to provide. The data for this asteroid comes from the NASA Center for Near-Earth Object Studies, the agency that tracks orbital information for every known near-Earth object. The system is genuinely impressive. Thousands of objects catalogued, trajectories computed, close approach tables updated continuously. When a new asteroid is discovered, the first priority is always the orbit. Get the trajectory pinned down. Determine whether it poses any collision risk on known future paths. That part of the system works remarkably well. What comes after the orbit? The physical characterization, the size, the shape, the composition, that is a different story entirely, and it takes considerably longer, requires different tools, and in many cases simply never happens at all. So here is where we are. An asteroid is about to pass between Earth and the Moon. It was discovered days ago. Its orbital path is well understood. Its size is completely unknown. And before you assume this is some kind of unusual emergency, you should know something that will make this feel considerably stranger. 2026 EG1 is not even the only one this week. There are 9 asteroids making close approaches to Earth in roughly the same window. 9. And not a single one of them has a confirmed physical characterization. Not one. That is not a headline from a conspiracy website. That is what the public asteroid database actually shows, right now, tonight. as this rock carves its silent path across the inner solar system. Is this a routine flyby that will pass without incident? Almost certainly yes. The odds overwhelmingly favour it being small, harmless, and completely unremarkable in physical terms. But here is the question that keeps planetary defence scientists awake at night, and the one that should honestly give all of us at least a moment of pause. How would tonight look any different if the answer were no? Part 2. The sub-lunar flyby that almost no one noticed. Hundreds of asteroids pass between Earth and the Moon every single year, and almost none of them make the news. That is not negligence, it is statistics. The overwhelming majority of objects that slip through the Earth-Moon corridor are small enough that even a direct atmospheric entry would produce nothing more dramatic than a bright fireball, a flash in the sky, a few sonic booms, maybe a handful of meteorite fragments scattered across a remote field somewhere. Nobody gets hurt. Nobody really notices. The solar system is full of debris, and most of it is genuinely boringly harmless. 2026 EG1 belongs to a category called Apollo asteroids, and understanding what that means tells you something important about why this object keeps coming back into Earth's neighbourhood. Apollo asteroids have orbits that cross Earth's path around the Sun. Their semi-major axis, the average distance from the Sun, across their entire orbit, is larger than Earth's. But because their orbits are elliptical, they dip inward and intersect the region where Earth travels. Think of it like two runners on different oval tracks. Most of the time they are nowhere near each other, but at certain points in each lap, they pass through the same stretch of track. The relative velocity of 2026 EG1, 9.6 km per second, is worth pausing on. The average near-Earth asteroid passes Earth at something closer to 18 km per second. This one is slower, which sounds reassuring but actually carries its own implication. A slower relative velocity means the object's orbit is more similar to Earth's in terms of energy and inclination. Objects like this tend to be gravitationally nudged by Earth's gravity over long timescales. They return, they revisit. Now let us actually visualize 318,000 kilometers, because human brains are genuinely terrible at processing distances at this scale. The Moon, on average, sits 384,400 kilometers away. Geostationary satellites, the ones that handle your television signals and much of your telecommunications, orbit at 42,164 kilometers. The International Space Station orbits at roughly 420 kilometers altitude. So 2026 EG1 at 318,000 kilometers is passing about 7 to 8 times farther out than the satellites you rely on every day, but still comfortably inside the Moon's orbital distance. That distinction matters. The phrase "closer than the Moon" lands in the human brain somewhere between concerning and terrifying, but the actual geometry is less dramatic than it sounds in a headline. The asteroid is not threading a needle. It is not skimming the upper atmosphere. It is, in cosmic terms, a comfortable miss. And yet, the trajectory is not what makes tonight worth paying attention to. The orbit is known. The position is calculable. The path of this asteroid, from the moment of discovery to the moment of closest approach, has been computed with the kind of precision that should honestly be considered one of the quiet triumphs of modern astronomy. A rock in space discovered days ago, and we can tell you its position to within seconds and kilometers across millions of kilometers of distance. That is extraordinary. What is not extraordinary, what is in fact a perfectly ordinary gap in our knowledge, is that nobody can tell you what it is made of, how large it actually is, or what it would do if it ever did hit something. The diameter field is blank. The albedo, the reflectivity of its surface, is unknown. Even the most basic physical facts about this object remain unconfirmed in the public record as it makes its closest approach tonight. Orbital mechanics and physical characterization are two very different sciences, conducted with very different tools, on very different timescales. One of them is working beautifully tonight. The other one never got started. And that gap between knowing exactly where something is and having no idea what it actually is going to matter a great deal more before this story's over. Part 3. The Size Ladder. From Pebble to City Killer. The size of an asteroid is not an academic detail. It is the entire ballgame. Everything else, the velocity, the angle of entry, the composition, feeds into the final calculation. But size is the variable that determines whether an incoming asteroid is a light show or a civilization-ending event. And the difference between those two outcomes is not measured in orders of magnitude. It is measured in tens of meters. On February 15, 2013, a rock approximately 20 meters wide entered Earth's atmosphere over the Russian city of Chelyabinsk. It did not hit the ground. It exploded in the air at an altitude of around 30 kilometers, releasing energy estimated at between 440 and 500 kilotons of TNT equivalent. That is roughly 30 times the energy of the Hiroshima bomb, detonated in the sky over a populated region. More than 7,000 buildings were damaged. Approximately 1,400 people were injured, most of them by shattered glass from windows blown inward by the pressure wave. A 20-meter rock, an airburst, no ground impact. Go back a little further, to June 30th, 1908, over a remote stretch of Siberian forest near the Podkamenia Tunguska River. The object that day was estimated at somewhere between 50 and 100 meters in diameter. Same story, it never hit the ground. It exploded in the atmosphere, but the energy release flattened approximately 2,150 square kilometers of forest. Trees were knocked flat in a radial pattern extending outward from the epicenter, like matchsticks pushed over by a giant hand. If that event had occurred over a major city instead of uninhabited Siberian forest, it would be among the deadliest disasters in recorded human history. So here is the size ladder that planetary defense scientists actually think in terms of. Objects under 10 meters almost always burn up completely during atmospheric entry. Objects between 10 and 20 meters can produce airbursts, explosions above the ground, with regional blast effects. Objects between 50 and 100 meters cause regional devastation on the scale of the Tunguska event. And at 140 meters, an asteroid earns a formal classification, potentially hazardous asteroid. That designation exists because an object of that size or larger, striking at the wrong angle and in the wrong location, could produce casualties on a scale that would redefine the word catastrophe. Now, the question you're almost certainly asking is, how do scientists normally figure out an asteroid's size in the first place? The primary method uses something called absolute magnitude, designated with the letter H in astronomical notation. Absolute magnitude measures how bright an object appears at a standardized distance and angle. Combine that brightness measurement with an assumption about the object's reflectivity, called albedo, and you can calculate a diameter range. The problem is that albedo varies enormously. Some asteroids are almost as dark as coal, reflecting only a few % of sunlight. Others are almost as bright as fresh snow. An asteroid with an unknown albedo can have a diameter estimate that varies by a factor of 5 or more depending on which assumption you use. A dark asteroid and a bright asteroid can produce the exact same brightness reading from Earth while being dramatically different in actual physical size. And in the case of 2026 EG1, there is currently no published brightness measurement detailed enough to produce even that uncertain estimate. The database entry that should contain the diameter sits empty, not because the calculation produced an unclear answer, but because the observation pipeline that feeds the calculation has not yet produced the input data needed to run it. Statistically, most close approach asteroids are small. The distribution of asteroid sizes heavily favours objects under 20 meters. If you pick a random newly discovered near-Earth asteroid, the probability is high that it is relatively tiny. But probability is not certainty. And certainty, when the alternative is a Tunguska-scale event over a populated region, is the only acceptable standard. Which raises the natural question, is this just one unlucky data gap, or is there something more systematic happening this week? Part 4, the 9 asteroid week. Let us zoom out, because the story of 2026 EG1 becomes considerably more interesting once you realise it is not travelling alone. In the same week as tonight's flyby, 8 other asteroids are making close approaches to Earth, 9 total if you count EG1. And when you pull up each of their entries in the public catalogue, when you look for the physical characterization data, the diameter estimates, the albedo values, the compositional analysis, you find something consistent and unsettling. Almost nothing is there. Not for most of them. In many cases, the physical data fields are either empty or populated with ranges so wide they are nearly meaningless. Take 2026 ET, another asteroid making a close approach in this same window, discovered recently. Orbit reasonably well constrained. Physical data, thin at best. Then there is 2015 VO142, discovered over a decade ago, making a return pass, and still lacking detailed physical characterization in the public record. And 2007 EG, discovered nearly 2 decades back, named and tracked, with an orbital history that spans multiple close approaches to Earth and still waiting in the queue for someone to get a good physical measurement. This is not a scandal. It is important to say that clearly. This is not evidence of incompetence or negligence. It is evidence of something arguably more frustrating, a resource problem masquerading as an information problem. Here is how asteroid characterization actually works. The orbital determination, the trajectory calculation, can be done with relatively modest optical telescopes. A few nights of positional observations, processed through sophisticated software, and you have an orbit. That part of the pipeline is well-funded, well-practiced, and reasonably efficient. The discovery surveys are finding new objects at an impressive rate. Physical characterization is a completely different operation. To get a reliable size estimate, you ideally want infrared observations, because infrared brightness correlates more directly with physical size than visible light does. You want spectroscopic data to identify composition. And for the most accurate size and shape measurements, you want radar observations, which means getting access to facilities like the Goldstone Solar System radar in California, a genuinely remarkable piece of infrastructure that can bounce microwave signals off asteroids and measure the returning echo with extraordinary precision. The problem is that radar time is among the most limited and oversubscribed resources in all of planetary science. There is simply far more demand for characterization observations than there is telescope time available to provide them. Hundreds of newly discovered asteroids cycle through Earth's neighborhood every year. A small fraction receive radar observations. A somewhat larger fraction get meaningful infrared measurements. The majority end up with orbital data and not much else. This creates what scientists sometimes call a characterization gap, a growing catalogue of objects whose positions are precisely known, whose physical nature remains largely mysterious. The catalogue gets longer every year as discovery surveys find more objects. The characterization backlog grows alongside it, and so we arrive at a week where 9 asteroids are passing Earth, and the physical data is sparse across the board. This is not a conspiracy, it is a budget. It is a scheduling problem. It is what happens when the detection half of planetary defense runs faster than the characterization half. The question this raises is a genuine one. In that gap between knowing an orbit and knowing a size, how much risk actually lives? The answer, it turns out, involves not just astronomy, but the sun itself, which tonight is doing something of its own. Part 5, the solar storm, arriving the same day. On the same day that 2026 EG1 makes its closest approach to Earth, our planet is being hit by something else entirely, and the fact that almost nobody is talking about both of these things simultaneously is itself a small illustration of how poorly equipped human intuition is for processing the actual environment in which this planet operates. The NOAA Space Weather Prediction Center, the agency responsible for monitoring and forecasting conditions in the near-Earth space environment, the civilian infrastructure that sits between the sun's behavior and the satellite operators, power grid managers, and aviation authorities who need to know about it, issued a forecast for a G1 geomagnetic storm coinciding with the asteroid's passage. The timing is coincidental. The two events have no physical relationship to each other. The solar wind stream causing the storm and the asteroid making its close approach are entirely independent phenomena that happen to be affecting Earth's environment on the same calendar date. But coincidence or not, the overlap creates a night that is worth examining carefully, because it reveals something about the texture of the space environment that Earth actually inhabits, rather than the calm, empty backdrop that most people imagine when they think about space at all. The source of tonight's storm is not the kind of solar event that generates dramatic news coverage. It is not a solar flare, the intense burst of electromagnetic radiation that erupts from active regions on the sun's surface and travels to Earth at the speed of light, arriving in 8 minutes. It is not a coronal mass ejection, the enormous bubble of magnetized plasma that explosive solar events hurl into the solar system, and that, when directed at Earth, can produce the most severe geomagnetic disturbances in the modern record. Both of those event types tend to generate headlines when they are large enough, partly because they are visually dramatic in solar observatory footage, and partly because the most powerful versions are genuinely capable of causing significant disruption to technological infrastructure. Tonight's storm comes from something called a coronal hole high-speed stream, which is a less cinematic phenomenon but one that is, in its own way, a more fundamental expression of how the sun actually works on a continuous basis rather than just during explosive events. A coronal hole is a region on the sun's surface, more precisely in the sun's corona, the diffuse outer atmosphere that extends millions of kilometers above the visible surface, where the magnetic field geometry is fundamentally different from the surrounding regions. In most parts of the corona, magnetic field lines form closed loops, arching upward from one region of the surface and returning to another, trapping plasma within them and preventing it from escaping into interplanetary space. These closed field regions are what you see as the bright structured features in ultraviolet and X-ray images of the sun, loops and arches of glowing plasma following magnetic field lines like iron filings around a bar magnet. In coronal holes, the magnetic field lines do not close, they open outward into space, extending away from the sun without returning, allowing the solar wind, the continuous stream of charged particles that the sun sheds in all directions, to escape more freely and more rapidly than it can from closed field regions. The solar wind that pours out through a coronal hole travels at speeds that can reach 600 to 800 kilometers per second, compared to the 300 to 400 kilometers per second, typical of the slower background solar wind from closed field regions. When you picture a coronal hole, imagine a region where a valve has been opened, where the magnetic containment that normally holds the plasma back has been released, letting it flow outward at higher pressure and higher velocity. When the sun rotates, and it rotates once every approximately 25 days at its equator, somewhat slower at higher latitudes, a coronal hole sweeps through space like a sprinkler rotating on a lawn. The high-speed stream it produces does not travel in a straight line from sun to Earth. It fans outward as the sun rotates, creating a curved structure in the solar wind called a corrotating interaction region, where the fast stream catches up to the slower solar wind ahead of it and compresses it, creating a region of enhanced magnetic field and particle density that sweeps past Earth with a predictable cadence tied to the sun's rotation period. Space weather forecasters can identify coronal holes in solar observatory images and predict with reasonable accuracy when the associated high-speed stream will arrive at Earth, typically 1 to 4 days after the hole rotates to face Earth's direction. When the high-speed stream arrives and presses against Earth's magnetic field, the magnetosphere, the invisible protective bubble generated by the planet's internal dynamo, it compresses the day side of the magnetosphere and stretches the night side into a long tail. The interaction between the solar wind's magnetic field and Earth's magnetic field transfers energy into the magnetosphere, driving electrical currents that flow through the upper atmosphere, heating it, expanding it slightly, and generating the electromagnetic variations on the ground that sensitive instruments detect as a geomagnetic storm. The severity scale runs from G1 to G5, and understanding what the full range looks like helps calibrate what G1 actually means. A G5 geomagnetic storm is a civilization-scale event in the modern technological era. The most famous modern example is the March 1989 storm, which induced electrical currents in the long transmission lines of the Hydro-Quebec power grid in Canada and caused protective relays to trip in a cascade failure that blacked out the entire province of Quebec for 9 hours. 6 million people lost power. The storm also damaged or disrupted satellites, confused navigation systems, and produced auroras visible as far south as Texas and Florida. A repeat of the 1989 event today, with modern society's far greater dependence on satellite infrastructure and interconnected power grids, would produce disruption on a scale that emergency management planners genuinely consider a major infrastructure risk. A G4 event can disrupt GPS systems enough to affect precision navigation, damage satellite electronics through enhanced radiation exposure, and force airlines to reroute polar flights that rely on high-frequency radio communications that geomagnetic storms disrupt. A G3 produces noticeable effects on power grid voltage, intermittent satellite navigation problems, and aurora visible from mid-latitude locations well below the Arctic Circle. A G1 is the mild end, the entry level, the meteorological equivalent of a light drizzle on a day when the forecast mentioned a small chance of rain. At G1 intensity, the expected effects include minor fluctuations in satellite drag, the slight increase in atmospheric density from geomagnetic heating that changes the orbital decay rate of low Earth orbit satellites by small amounts that operators account for in their station-keeping calculations, slight reductions in GPS positioning accuracy at high latitudes, where the signal passes through the most disturbed portion of the ionosphere, possible interference with high-frequency radio communications used by aviation and amateur radio operators in polar regions, and auroras, the northern and southern lights, potentially visible from locations in the northern tier of the continental United States, roughly above 45 to 50 degrees latitude, if skies are clear and light pollution is low. It is, by the operational standards of space weather forecasting, a routine event that happens multiple times per year and generates internal agency notifications rather than public emergency alerts. To be precise about the thing that conspiracy-adjacent coverage of tonight's events will almost certainly get wrong, a G1 geomagnetic storm does not meaningfully threaten asteroid tracking operations. This is worth stating clearly because the coincidence of a geomagnetic storm and an asteroid close approach on the same night is exactly the kind of narrative conjunction that generates speculative content suggesting the two events are interfering with each other, or that the storm is disrupting the measurements, or that something is being hidden behind the electromagnetic noise. None of this is accurate. The optical telescopes used by Discovery surveys are ground-based instruments that collect light passing through the atmosphere. They are not affected by geomagnetic activity in any operationally significant way. The radar facilities used for asteroid characterization operate at radio frequencies, managed to avoid interference from ionospheric disturbances. The blank diameter fields in tonight's asteroid catalogue exist for reasons that have nothing to do with a geomagnetic storm and everything to do with the characterization pipeline limitations that this entire story has been examining. The storm is, for the purposes of tracking 2026 EG1 tonight, essentially irrelevant in practical terms. The two events share a date and nothing else, but the coincidence does something that is worth sitting with even after the practical irrelevance is established. It layers a second invisible phenomenon onto an already poorly understood one, and in doing so it creates a moment that accurately represents the actual environment in which this planet exists, rather than the simplified version that daily life encourages us to imagine. Two things are happening tonight that the overwhelming majority of people on Earth have no awareness of. An asteroid is completing its passage between Earth and the Moon, its diameter unknown, its physical nature uncharacterized, its existence in the catalogue a matter of days. A stream of energetic particles accelerated by the Sun's rotating magnetic geometry is pressing against the magnetosphere, inducing currents in the upper atmosphere, creating the conditions for auroras at high latitudes. Both phenomena are detectable only with specialized instruments. Both are completely invisible without those instruments. Both are, in isolation, manageable, one almost certainly small and harmless, the other definitionally minor on the storm severity scale. Together they create a night that is an unusually honest portrait of what Earth's actual situation is in the solar system. Not a planet floating in protective emptiness, isolated from the turbulent processes of its stellar neighborhood. An active participant in a dynamic, continuously variable space environment, bombarded by solar wind, swept by energetic particle streams, crossed by rocky debris on orbital paths that sometimes intersect its own, embedded in a solar system that is far more eventful than the stillness of a clear night sky suggests. The G1 storm will fade over the next day or two, as the high-speed stream passes and the solar wind returns to background conditions. The asteroid will continue its outbound arc, decelerating relative to Earth, receding into the inner solar system on the long curve back toward the Sun. Both events will be logged, archived, and largely forgotten by the infrastructure that recorded them. And the question that reasserts itself in the quiet after both phenomena have passed is not about either of them specifically. It is about the nights, and there will be nights, when something approaches from a direction that neither the geomagnetic monitoring network nor the asteroid detection surveys can see, arriving not with a G1 forecast and a catalogue trajectory, but with no warning at all, from the one direction in the solar system where the lights are permanently off. Part 6. The sunward blind spot. There is a direction in space from which a dangerous asteroid could approach Earth, and ground-based telescopes would be functionally unable to see it until it was too late to do anything at all. That direction is toward the Sun. It sounds almost too simple to be the central vulnerability in the entire planetary defense architecture. It sounds like the kind of thing that should have an obvious fix, a workaround, some clever engineering solution that addresses the problem without requiring anything too dramatic. It is not that kind of problem. The sunward blind spot is not a design flaw in any particular telescope or survey system. It is a geometric constraint imposed by the fundamental physics of operating an optical observatory on the surface of a planet that orbits a star. Ground-based optical telescopes observe the night sky. They look away from the sun by definition, because the sun's light, a star 150 million kilometers away, pouring 4 times 10 to the 26th watts of electromagnetic radiation into the surrounding space, overwhelms any sensor pointed anywhere near it. You cannot image a faint dark asteroid against the glare of a star that is 30 billion times brighter than the object you're trying to find. The physics do not allow it. The geometry of the problem is worth understanding in some detail, because it explains not just why the blind spot exists, but why it is specifically dangerous for a certain category of threatening object. Earth moves along its orbit at approximately 29.8 kilometers per second, with the sun always located in one general direction from Earth's perspective at any given moment. The night side of Earth, the hemisphere facing away from the sun, is where ground-based telescopes do their work. This means that surveys systematically cover the sky in the hemisphere pointing away from the sun, and systematically cannot cover the hemisphere pointing toward it. An asteroid approaching Earth from the inner solar system, one whose trajectory keeps it geometrically close to the Sun-Earth line as seen from our perspective, will spend its final approach period in the zone where the sun's glare dominates the sky background. As it gets closer to Earth and the geometry tightens, it moves deeper into the unobservable region. The closest approaches of such objects occur when they are also at their most hidden. By the time the object clears the solar glare zone sufficiently to be detectable by ground-based surveys, which happens after it has passed Earth and is now receding, with the geometry opening up as it moves away, the encounter is over. The asteroid that was approaching is now departing, and the observation that could have provided warning is now only documentation of something that already happened. This is not a theoretical vulnerability constructed to illustrate a point. It is a documented, specific, historically demonstrated failure mode of the current detection architecture, and it has a date attached to it. February 15th, 2013, over the Russian city of Chelyabinsk. The Chelyabinsk meteor entered Earth's atmosphere at approximately 19 kilometers per second at a shallow angle, approximately 18 degrees from horizontal. It was travelling from the general direction of the Sun, the global network of asteroid detection surveys operating in 2013, which included multiple dedicated near-Earth object search programs running on large telescopes with automated pipelines, representing the most capable ground-based planetary defense infrastructure that had ever existed up to that point, had 0 prior observations of the object, not a single detection in the days or weeks before impact, not a candidate observation that was later identified in archival data. 0. The object's existence in Earth's vicinity was unknown to the detection network until it announced itself by blazing across the sky at 9:30 local time on a February morning over a city of 1 million people. The first records of its existence were dashboard camera videos, the ubiquitous Russian dashcam footage that captured a streak of light bright enough to cast shadows, brighter than the sun at its peak, moving across the sky and terminating in an airburst that released energy estimated at between 440 and 500 kilotons of TNT equivalent. The pressure wave from the explosion travelled outward and struck the city approximately 2 to 3 minutes after the airburst, shattering windows across an area of thousands of square kilometres. More than 7,000 buildings were damaged. Approximately 1,400 people were injured, the overwhelming majority from glass lacerations as windows exploded inward. A zinc factory roof partially collapsed. The injured included people who had been drawn to their windows by the bright light of the fireball and were then struck by the pressure wave that arrived minutes later, a sequence of events that, if you did not know it was an asteroid, would be deeply confusing and terrifying in real time. The Chelyabinsk object was approximately 20 meters in diameter. 20 meters. A rock the size of a modest office building, releasing energy equivalent to 30 or more nuclear weapons of the Hiroshima scale, causing over 1,000 injuries in a city that had no warning it was coming, because the detection system that should have found it was geometrically prevented from seeing it by the position of the sun. Now hold that scenario in your mind and walk the size ladder upward. The Chelyabinsk object was 20 meters. The Tunguska impactor in 1908 was estimated at 50 to 100 meters, 2.5 to 5 times larger in diameter, which translates to 15 to 125 times more mass, depending on where in that range the actual size fell, which translates to energy release potentially orders of magnitude larger. The Tunguska event flattened over 2,000 square kilometers of Siberian forest. If it had occurred over a city, the casualties would have been catastrophic by any historical standard of disaster. Scale up further to 80 meters approaching from the sunward blind spot on an approach geometry similar to Chelyabinsk. Same zero advance warning from ground-based surveys. Same discovery timeline, which is to say no discovery timeline, because there is no discovery until the object enters the atmosphere and the dashcam footage starts uploading. The energy release of an 80-meter object is not a regional nuisance. It is a regional catastrophe, and the window for any kind of organised civil defence response, evacuation, shelter-in-place advisories, emergency management activation is measured in the minutes between when the fireball first appears in the sky and when the pressure wave arrives. That is not a response window. That is barely enough time to be frightened. The detection community has improved significantly since 2013, and this deserves honest acknowledgement rather than being buried under the weight of the blind spot discussion. Survey systems are more capable, camera fields are larger, processing pipelines are faster, more skies covered more often. The completeness of the near-Earth object catalogue at larger size ranges has improved substantially, and objects that would have been unknown in 2013 are now tracked and characterised. The lead times for known threats have improved because the inventory of known threats has grown. None of this closes the sunward blind spot. Improved ground-based surveys cover the accessible sky better than ever before. They cannot cover the sky that the sun makes inaccessible, because the inaccessibility is geometric rather than instrumental. A larger telescope pointed at the same unobservable region produces a more detailed image of glare. A faster processing pipeline applied to unobservable data produces faster confirmation that the data is unobservable. The constraint is not the quality of the instruments. It is the location of the observers relative to the star they orbit. There is an additional subtlety to the blind spot that makes it specifically dangerous for the category of objects most likely to produce short warning close approaches. Apollo asteroids, the orbital class that includes 2026 EG-1, have orbits that cross Earth's path from the inner solar system. Their trajectories frequently bring them inward from the sunward direction. The very orbital geometry that makes them Earth crossers also tends to make their close approach. Phases occur while they are in or near the solar glare zone. The asteroids most likely to encounter Earth are, by virtue of that same orbital geometry, disproportionately likely to approach from the direction that ground-based surveys cannot monitor. This is not a coincidence. It is a consequence of orbital mechanics, and it means the blind spot is not a random sample of the threat population. It preferentially hides the objects that are most relevant to planetary defense. The solution to this problem is not complicated in concept, even though it has proven complicated in practice. You cannot observe the sunward blind spot from Earth's surface. You can observe it from a different location. Specifically, you can observe it from a spacecraft in solar orbit positioned such that its line of sight to the inner solar system is not blocked by Earth's sun-facing hemisphere and not overwhelmed by the sun's proximity. An infrared telescope in such an orbit, one that detects asteroids by their thermal emission rather than reflected sunlight, eliminating the albedo uncertainty problem at the same time as it addresses the viewing geometry problem, would have access to exactly the region of sky that ground-based surveys cannot reach. That solution has a name, it has a mission design, it has a projected launch window. It has been in development for over 15 years, waiting for the funding stability that would let it fly. Whether it reaches orbit before something significant arrives from the direction it was designed to watch is the question that gives planetary defense scientists a specific, focused, very well justified form of anxiety. But before we get to the mission that would fix the blind spot, it is worth spending a moment with a specific documented example of what the blind spot looks like when it operates in practice, not with a 20-meter rock over a Russian city, but with an object that passed closer to Earth than most of the satellites currently in orbit, detected only after the encounter was already over. Part 7. The Asteroid. We detected too late. In October 2025, an asteroid designated 2025 TF passed approximately 428 kilometers above Antarctica, and the planet did not notice. Not because the event was suppressed or classified or handled quietly by agencies that preferred not to discuss it. because the detection systems that are supposed to find these objects before they arrive found this one after it had already left. The asteroid slipped through the space between Earth and the orbital altitude of crewed spacecraft, completed its closest approach to the planet, and then began receding into the outer solar system, and it was during that recession, as it moved away from Earth rather than toward it, that telescopes finally picked it up and logged the encounter that had already happened. 428 kilometers. The number requires context to land properly, because in everyday terms it sounds like a large distance, and in astronomical terms it is essentially contact. The International Space Station maintains an orbital altitude of roughly 420 kilometers above Earth's surface, varying slightly as atmospheric drag causes gradual decay between periodic reboost maneuvers. The altitude changes depending on the phase of the solar cycle. Solar maximum expands the upper atmosphere, increasing drag, requiring more frequent reboosting to maintain the station's orbit. But 420 kilometers is a reasonable working figure for where human beings currently live and work in space. 2025 TF passed at 428 kilometers above Antarctica, 8 kilometers higher than the typical orbital altitude of the International Space Station. If the geometry had been slightly different, if the approach angle had brought the object over a populated region instead of the Antarctic continent, if the trajectory had been depressed by a few kilometers, the encounter would have been an atmospheric entry rather than a flyby, and the detection network would still not have known it was coming, because the detection network did not know it was there at all until the encounter was over. This is worth sitting with beyond the dramatic framing, because the specific mechanism of the failure tells you something important about the structural limits of the current detection architecture, rather than just the outcome of one unlucky night. 2025 TF was discovered on its way out, not approaching, receding. Telescopes detected it as a moving point of light in the days after its closest approach, identified its motion as consistent with a near-Earth object, and submitted the observations for orbital calculation. The orbital solution confirmed what the motion suggested. This object had recently made an extremely close pass of Earth, closer than low Earth orbit, and had done so without appearing in any pre-encounter survey data. The flyby was documented in hindsight. The catalogue entry was written in retrospect. The encounter happened in the present tense and was recorded in the past tense. The reason the post-encounter detection was possible while the pre-encounter detection was not comes down to viewing geometry and the specific characteristics of close approaching small objects that make them systematically difficult to find before they arrive. When 2025 TF was approaching Earth, inbound, on the portion of its trajectory that brings it to closest approach, its angular motion across the sky, as seen from Earth's surface, was increasing rapidly as the distance decreased. Objects on close approach trajectories speed up in apparent motion as they close, eventually moving so fast across the sky that they streak across survey images rather than appearing as point sources, making automated detection pipelines less effective. At the same time, the approach geometry may have placed the object in sky regions with higher background source density, or in regions observed less frequently by the survey cadence, or in regions affected by the sunward blind spot discussed in the previous section. After closest approach, the geometry reverses. The object is now moving away from Earth. Its apparent motion across the sky slows as distance increases. It becomes a more tractable target for survey instruments looking for moving point sources at angular rates consistent with solar system objects. The object that was uncatchable on approach becomes detectable in recession, but the encounter it was uncatchable for is already over. 2025 TF was almost certainly very small. The post-encounter observations that established its existence also provided the data for a rough size estimate, and the numbers suggest an object perhaps a few meters across, possibly up to 10 or 15 meters at the most generous interpretation of the available data. In that size range, an atmospheric entry would most likely have produced a fireball and airburst, rather than a ground impact, a bright streak across the sky, a pressure wave, possibly some small meteorite fragments scattered across a remote area. The Antarctic location of the closest approach means that even an atmospheric entry scenario would have occurred over one of the least populated regions on Earth's surface, reducing the probability of any human consequence to very near zero. The odds of a harmful outcome from 2025 TF specifically were genuinely, defensibly very low. This is the honest assessment, and it matters to state it clearly rather than allowing the dramatic framing of the distance figure to imply a level of danger that the object's probable size does not support. But the size of 2025 TF is not what makes its encounter important. What makes it important is that the detection gap that allowed it to pass unobserved is not calibrated to the size of the object passing through it. The gap exists because of approach geometry, apparent motion characteristics, survey cadence limitations, and the fundamental detection physics that make small, fast, close-approaching objects systematically harder to find before their encounters than after them. Those factors operate identically regardless of whether the object is 5 meters wide or 50 meters wide or 150 meters wide. The detection failure mode that produced a post-encounter discovery for 2025 TF would produce exactly the same post-encounter discovery, or no discovery at all, for a considerably more consequential object approaching on a similar trajectory. This is the proof-of-concept character of the encounter that planetary defense analysts focus on when they discuss cases like 2025 TF. Not the specific risk from that specific object, which was low. The demonstrated existence of an approach geometry and size regime that the current detection architecture handles poorly, combined with the demonstrated possibility of an object in that regime passing at satellite orbital distances without pre-encounter detection. The two facts together describe a vulnerability that the size of 2025 TF happened to make harmless on this particular occasion, but would not make harmless in general. Why does this vulnerability exist at the systematic level rather than just as an occasional unlucky outcome? The answer involves several converging factors that compound each other in ways that make the problem harder than any single factor would suggest. Faintness is the first factor. Asteroid brightness scales with the square of the diameter. An asteroid 10 meters wide reflects 100 times less light than an asteroid 100 meters wide at the same distance, because it presents 100 times less surface area to the Sun. This means that as you go down the size ladder towards smaller objects, the distance at which a survey telescope can detect them decreases rapidly. A survey that can find a 100-meter asteroid at a distance of several million kilometers might only be able to find a 10-meter asteroid when it is within a few 100,000 kilometers, which is, for fast-moving objects on close approach trajectories, a very short warning time. The objects most likely to slip through pre-encounter detection are exactly the ones that are too faint to see until they are too close to provide meaningful warning. Apparent angular velocity is the second factor, and it interacts with faintness in a compounding way. As a close-approaching asteroid gets nearer to Earth, two things happen simultaneously. It gets brighter because it is closer, which should make it easier to detect, and it moves faster across the sky in apparent angular terms, which makes it harder to detect with standard survey pipelines, optimized for objects moving at the rates typical of more distant asteroids. Automated detection systems identify moving objects by comparing source positions across images taken at fixed time intervals and flagging sources that have moved by amounts consistent with solar system objects at plausible distances and velocities. Objects moving significantly faster than the expected range, which close-approaching small asteroids often do in their final hours before closest approach, can fall outside the parameter space that automated pipelines are tuned to catch. Sky coverage cadence introduces a third layer of vulnerability. Survey systems observe each patch of sky on a schedule, returning to the same region every few nights under typical operating conditions. An object that is only detectable at the distances corresponding to short warning times might enter the detectable distance range between two scheduled observations of the relevant sky region, make its closest approach during that gap, and be detected in recession before the next scheduled observation of the approach direction occurs. The cadence that is perfectly adequate for finding larger, more distant objects creates windows of vulnerability for smaller, faster-moving ones. The result of these compounding factors is a category of encounters that sits in a regime the current detection architecture handles fundamentally poorly. Not through any specific failure of the systems involved, but through the accumulated limitations of instruments and pipelines designed around the detection physics of larger, slower objects applied to a population of smaller, faster ones. 2025 TF demonstrated this regime exists, and that objects within it can pass at distances that would put them in low Earth orbit if the trajectory was slightly different, without triggering any pre-encounter alert. The system catches most of what is catchable with current ground-based optical infrastructure. What is not catchable from the ground, the sunward approaches, the far small objects in the close approach detection gap, the objects that arrive before the survey cadence has a chance to find them, forms its own quiet, invisible category in the risk landscape. And the reason that category is more concerning than it might initially appear brings us back to a question that tonight has illustrated with unusual clarity: size. Because determining the size of an object that has already passed is considerably easier than determining the size of one that is currently approaching, and the tools required to measure size accurately before an encounter, in time for the measurement to actually matter, are in far shorter supply than the planetary defense conversation typically acknowledges. Part 8: Why size is harder than orbit. Knowing where something is and knowing what something is turn out to require completely different sciences, different equipment and different investment levels, and the gap between them explains most of what you have seen this week, most of what the catalogue shows tonight, and most of what planetary defense still needs to solve before it can honestly claim to be complete. The distinction sounds like it should be minor. Position and size are both physical properties of the same object. Measuring one should be roughly as straightforward as measuring the other. In practice, the two measurements are so different in their technical requirements that they might as well belong to separate disciplines, and in a meaningful sense they do. Astrometry is the science of position, and it is the foundation on which everything else in asteroid tracking is built. To determine an asteroid's orbit, you need multiple precise measurements of its location against the fixed background of stars, taken across a baseline of several nights, fed into orbital computation software that fits a mathematical trajectory to the observed data points. The telescopes needed for this work are optical instruments, cameras attached to mirrors or lenses, collecting the light reflected from the asteroid's surface and recording where that light appears against the starfield. They do not need to be enormous. They do not need exotic detector technology. They need to be stable, well-calibrated and capable of precise positional measurements across a field of view containing both the moving asteroid and the fixed reference stars used to establish its coordinates. The observation strategy scales well with automation in a way that makes astrometry tractable at the survey scale. A modern discovery pipeline takes a sequence of images of the same sky region, runs automated software that identifies all detected sources, compares source positions across images taken at different times, flags sources that have moved relative to the fixed star background, and submits the moving source candidates for further processing. The orbit calculation software takes the submitted positions and fits a trajectory. If the arc length is sufficient, if enough observations across enough nights constrain the solution adequately, the resulting orbit can be quite precise, even for a newly discovered object. This is why the orbital data for 2026 EG1 is well determined while the physical data is blank. The astrometry pipeline engaged immediately upon discovery and produced a reliable trajectory within hours. The physical characterization pipeline requires something different entirely. Photometry, measuring the brightness of an asteroid precisely enough to derive useful physical information, begins the transition into harder territory. Apparent brightness, measured carefully across multiple observations and converted into absolute magnitude using standardized calibration procedures, provides the primary input for size estimation in the absence of more direct measurements. The calculation is conceptually simple. Take the brightness, assume a reflectivity, calculate the diameter that would produce that brightness at that distance. The problem is the assumption. Asteroid reflectivity, albedo, varies enormously across the population. Some asteroids are among the darkest solid objects in the solar system, reflecting only 3 to 5% of incident sunlight. Their surfaces covered in organic compounds and carbon-rich minerals that absorb light with remarkable efficiency. Others are bright, rocky objects reflecting 30 to 40% of incident sunlight, their surfaces composed of silicate minerals that scatter light more readily. A dark asteroid and a bright asteroid of identical size will look dramatically different in reflected light. Conversely, a dark large asteroid and a bright small asteroid can produce identical apparent brightness readings from Earth. Without an independent constraint on albedo, a brightness measurement translates into a size range that can span a factor of 3 to 5 or more in diameter, which translates into a factor of 25 to 125 or more in volume, and roughly equivalent ranges in mass and impact energy. That is not a size estimate. That is a category of possibilities wide enough to span the distance between a harmless fireball and a regional catastrophe. Getting a useful albedo constraint requires additional observations, either infrared measurements that compare the asteroid's thermal emission to its reflected light, or spectroscopic observations that identify the mineralogical composition of the surface and constrain the reflectivity based on known properties of those minerals, or radar observations that provide size independently of any reflectivity assumption at all. Each of these requires different instruments, different scheduling, different expertise, and considerably more resources than the astrometry that established the orbit. Radar is where the physical characterization story becomes genuinely extraordinary in its capability and genuinely frustrating in its scarcity. Planetary radar astronomy works on a principle that seems almost audacious when you describe it plainly. You point a large radio telescope at an asteroid tens of millions of kilometers away, transmit a precisely shaped beam of microwave radiation toward it, wait for the signal to travel to the asteroid and back at the speed of light, and then analyze the returning echo with sufficient sensitivity to extract detailed physical information about a rock the size of a city block in the outer darkness of the inner solar system. The Goldstone Solar System Radar, located in California's Mojave Desert and operated as part of NASA's Deep Space Network, is one of the two primary facilities in the world capable of this work, the other being the Arecibo Observatory in Puerto Rico, which collapsed in December 2020, removing from service a facility that had been the most sensitive planetary radar instrument ever built, and that produced an irreplaceable fraction of the world's asteroid radar characterization data over its decades of operation. The loss of Arecibo was a significant setback for planetary radar astronomy that has not been fully compensated by other infrastructure, and its absence is felt in the characterization pipeline every time a close-approaching asteroid that would have been a good Arecibo target passes through the catalogue with its physical data unmeasured. When an asteroid is close enough and large enough to produce a detectable radar echo from Goldstone, the information content of the resulting dataset is incomparably richer than anything optical observations can produce. Radar can determine the asteroid's size with uncertainties of a few percent, rather than the factor of several uncertainties that plague optical size estimates. It can map the three-dimensional shape of the object by analysing how different parts of the surface produce echoes at slightly different times and slightly different frequencies as the asteroid rotates. It can determine the rotation rate and the orientation of the rotation axis. It can characterise the surface roughness at centimetre to metre scales from the statistical properties of the echo. And it can detect whether the asteroid is actually a binary system, a primary body with a smaller moonlet orbiting it, which turns out to be a surprisingly common configuration among near-Earth asteroids, with implications for both impact risk assessment and deflection planning. The limitation of radar is severe and twofold. The first constraint is physical. Radar signal strength decreases with the square of the distance in each direction. The transmitted beam spreads as it travels outward, and the reflected echo spreads again as it returns. The received echo power therefore drops with the fourth power of range. An asteroid twice as far away produces an echo 16 times weaker. An asteroid half as large at the same distance produces an echo with 1/4 the cross-section. Objects that are small and moderately distant, the Chelyabinsk scale impactors, the sub-30-metre objects that represent the most common category of potentially damaging atmospheric entrants, simply do not produce echoes strong enough to detect with current radar technology except during the closest approaches, which are precisely the situations where the warning time is already shortest. The second constraint is institutional. Goldstone is a national scientific asset with an observation schedule that is allocated through a competitive process balancing planetary radar science against the facility's other uses, including deep space communication support for active NASA missions. Radar time is not available on demand. A newly discovered asteroid that makes a close approach in 3 days cannot simply be inserted into the Goldstone schedule, because it would be interesting to characterize it. The scheduling lead time, the operational requirements, and the competing demands on the facility mean that many close approach asteroids pass through their optimal radar observation windows without receiving any radar observations at all. The result is a characterization pipeline that is genuinely capable, genuinely active, genuinely producing important science, and genuinely running far behind the discovery rate. There are thousands of near-Earth asteroids in the current catalogue that have never received any radar observation. Thousands more have been observed optically, but without the multi-geometry brightness measurements needed to constrain even a rough albedo estimate, leaving their sizes uncertain by factors that would be unacceptable in any other context, where the consequences of uncertainty were comparable. For every object that receives a thorough physical characterization, radar observations, infrared photometry, spectroscopic composition analysis, rotation light curve measurement, dozens of new objects enter the catalogue and join the waiting list, each bringing its own blank data fields to the growing inventory of what we know we do not know. 2026 EG1, discovered days ago, making its closest approach tonight at 318,000 kilometers from Earth, never had time to move through any part of the characterization pipeline. Not because the pipeline does not exist or does not work, because the pipeline requires lead time that the discovery timeline did not provide. Between the moment of discovery and the moment of closest approach, there was no window in which radar observations could have been scheduled, no infrared observation campaign could have been organized, no spectroscopic characterization could have been completed. The blank diameter field is not an oversight. It is the predictable output of a system where the time between discovery and encounter was shorter than the minimum time required for characterization to occur. In the space where the size measurement should be, where the albedo estimate should be, where the physical nature of the object should be described, there is instead a gap. And in that gap, as in every gap that human knowledge leaves open, something entirely predictable happens. The human mind, uncomfortable with uncertainty and pattern-hungry by deep evolutionary design, reaches for the nearest available explanation and begins constructing a story to fill the empty space. The stories it constructs around asteroid data gaps are specific, recurring, and worth understanding, not because they are true, but because the reasons they are compelling reveal something important about the difference between what the public perceives about planetary defense and what the actual system looks like from the inside. Part 9. The Conspiracy Narratives. Every time an asteroid flyby gets any public attention, and especially every time one involves data gaps or late discoveries, a predictable set of narratives emerges online within hours. The first is what you might call the withholding theory. The claim goes like this: agencies like NASA or the European Space Agency have the size data. They know exactly how large the asteroid is. They have decided not to release it because the information would cause panic. The blank diameter field is not a genuine gap, it is a redaction. This narrative is compelling for a specific reason. It requires the least technical knowledge to construct and the most technical knowledge to refute. Most people do not know that orbital determination and physical characterization are different sciences requiring different infrastructure. They do not know that albedo uncertainty produces size uncertainty even when brightness data exists. When they see a diameter field that is blank, the simplest human explanation is that someone chose to leave it blank, not that the measurement does not yet exist because the required observations have not occurred. The second narrative is the swarm hypothesis. 9 asteroids in 1 week, a geomagnetic storm on the same day. Something, the argument goes, is disturbing the outer asteroid belt. A gravitational anomaly, a rogue body, an event causing a synchronized cluster of close approaches. The universe does not produce coincidences, or so this version of events insists. The reality is substantially less cinematic. Close approaches happen continuously. The asteroid catalogue contains hundreds of thousands of objects, and at any given time, a meaningful fraction of them are on trajectories that will bring them near Earth's orbit within the coming weeks. Groupings of close approaches within a single week are not unusual. They do not require a common cause. They are what a densely populated solar system looks like when you watch closely enough. The third narrative tends to emerge specifically from the geomagnetic storm coinciding with the flyby. This version suggests the events are a coordinated test of emergency communication systems, or a cover for something being done in orbit, or a deliberate deception operation. The asteroid and the storm together are framed as a script with multiple actors. These narratives spread because uncertainty is uncomfortable, and a confident wrong answer often feels psychologically preferable to an honest acknowledgement of complexity. The blank data fields represent a real limitation, a genuine gap in the characterization system, and that gap is real enough to be alarming on its own merits. The conspiracy framing misidentifies the problem. The actual story, the one supported by the data, is less emotionally satisfying but considerably more actionable. The gaps exist because of funding priorities, resource constraints, and detection architecture limitations that can be specifically addressed. And the specific address that Planetary scientists have been fighting to put in place for over a decade is a mission that would change this story permanently if it ever actually launches. Part 10. The real problem: underfunded planetary defense. The sunward blind spot has a proposed solution. It has had one for years. It is called the NEO Surveyor. NEO Surveyor, where NEO stands for Near Earth Object, is a space-based infrared telescope designed to operate in a solar orbit that gives it a fundamentally different view of the solar system than anything ground-based can achieve. Its primary scientific capability is detecting asteroids via their infrared heat signatures rather than reflected visible light. And that distinction, which sounds like a technical footnote, is actually the entire reason the mission matters. Here is the physics. Asteroids absorb sunlight and re-radiate it as infrared heat. The infrared brightness of an asteroid correlates much more directly with its physical size than its visible brightness does, because the heat emission depends on the surface area of the object, which depends on its actual physical dimensions. The albedo problem, the uncertainty that makes visible light size estimates unreliable, the reason that two asteroids of completely different sizes can look identical in an optical telescope, largely disappears in the infrared. An infrared telescope sees a darker asteroid almost as clearly as a brighter one of the same size, because both emit heat in proportion to their surface area, regardless of how much light they reflect. You're no longer measuring how shiny something is, you're measuring how warm it is, and warmth scales with size in a way that shininess simply does not. This single capability shift would address one of the core problems illustrated by tonight's flyby. 2026 EG1 has a blank diameter field, not because nobody cares about its size, but because the optical brightness data needed to constrain even a rough estimate has not been gathered in time. An infrared observatory already in solar orbit, with a different viewing geometry and continuous survey capability, could potentially provide a meaningful size constraint on a newly discovered object far earlier in the timeline. The blank field problem does not disappear entirely, but it shrinks substantially. Operating in solar orbit rather than Earth orbit, NEO Surveyor would have a viewing geometry that covers the sunward approaches that ground-based surveys cannot access. The specific orbital design places the telescope in a position where it can observe asteroids moving against the sky background in directions that are currently hidden behind the Sun from Earth's perspective. Think of it as stationing a lookout on the other side of the wall that has been blocking the view. The blind spot as a concept would be dramatically reduced. Not eliminated, no single mission eliminates every detection gap, but reduced to a degree that would represent a genuine generational improvement in planetary defense capability. The projected scientific return is significant by any measure. Models suggest NEO Surveyor could detect the majority of near-Earth asteroids larger than 140 meters, the potentially hazardous threshold, the size above which an impact produces regional to continental scale devastation within its planned operational period of several years. It would also find large numbers of smaller objects that current surveys are missing entirely, the Chelyabinsk-scale rocks that arrive with little or no warning because they are simply too faint for existing ground-based systems to catch early. The characterization capability from infrared data would reduce the size uncertainty problem substantially, providing meaningful constraints on diameter, even for newly discovered objects that have not yet been observed by radar or studied with spectroscopy. The mission has been in development, in various forms and under various names, for a timeline that stretches back over 15 years. 15 years. The core scientific case for a space-based infrared asteroid survey was being made in the early 2000s, when the limitations of ground-based optical surveys were already well understood. The mission concept has survived multiple rounds of planetary science decadal surveys, program reviews, budget negotiations, and institutional restructuring. It has faced schedule slippages that pushed the projected launch date from the early 2020s to the mid-2020s to the current projected window in the late 2020s. Each slippage was driven not by scientific or engineering failure, but by the same thing that drives most government program delays: funding uncertainty and competing budget priorities. There is something genuinely strange about the situation when you look at it directly, and it is worth looking at directly. The cost of a mission like NEO Surveyor, a few $100 million across its full development and operational lifetime, is, in the context of federal budgets, an amount that rounds to a rounding error. We're talking about a fraction of a percent of the annual discretionary budget of the agencies involved. The United States spends more money on a single highway interchange project in a mid-sized city than the entire life cycle cost of a space-based planetary defense observatory. The cost of a single major motion picture production is comparable, a few $100 million spread across a decade of development and operations is not a number that should be difficult to find in a budget that runs into the trillions. The cost of failing to detect a 140-meter asteroid on a collision course, in lives, in infrastructure, in economic disruption, in the cascading consequences of a regional devastation event striking a populated area, is incalculable, not large, not expensive, incalculable. The Tunguska event, which involved an object estimated at 50 to 100 meters, flattened over 2,000 square kilometers of forest in 1908. Scale that up to 140 meters over a city of 5 million people, and the arithmetic becomes something that does not lend itself to calm discussion. The asymmetry between the cost of protection and the cost of the thing being protected against is so extreme that the budget argument against the mission has never made logical sense. It has never made logical sense, and yet the mission has spent 15 years in development waiting for stable funding, and the projected launch window keeps moving, and the blind spot remains open, and the characterization backlog grows, and 9 asteroids pass Earth this week with blank data fields, while the fix sits in a queue somewhere waiting for a line item to survive the next appropriation cycle. That is the situation. Not a conspiracy, not incompetence. A resource allocation problem so straightforward that its persistence is almost philosophically confusing. To be fair to the people working on this, progress is real. The NEO Surveyor mission has moved through development phases, hardware exists, teams are working, the scientific case has been made successfully enough that the mission is funded at some level and moving forward. The question is not whether it will launch. The current expectation is that it will, but whether it will launch on a timeline that reflects the actual urgency of the gap it is designed to fill, or whether it will continue to slip while the detection and characterization backlog grows alongside the discovery rate. Every year that the launch slips is another year of close approaches logged with incomplete characterization data, another year of blank diameter fields in the catalogue, another year of objects discovered days before their closest approach, with no time for any physical measurement to occur before the encounter is over. Another year of relying on statistical probability to reassure ourselves that the uncharacterized object passing between Earth and the Moon is almost certainly small, almost certainly harmless, almost certainly not the one that changes everything. Probability is a reasonable guide to planning. It is not a substitute for measurement, and measurement, for the objects approaching from the sunward blind spot, requires exactly the kind of infrastructure that NEO Surveyor is designed to provide, and that the current system does not have. Tonight, at 0327 Coordinated Universal Time, 2026 EG1 will pass 318,000 kilometers from Earth. Its diameter unknown, its albedo unmeasured, its physical nature a blank space in the catalogue. It will almost certainly be small, it will almost certainly pass without incident, and the system that allowed it to arrive uncharacterized will continue operating exactly as it has been, waiting for the resources and the timeline to become something more capable than what exists right now. The blind spot will still be open tomorrow morning. The characterization backlog will be slightly longer, and somewhere in a development queue, a space telescope that could address both of those problems is waiting for the bureaucratic and budgetary conditions that will let it fly. Here is the thought that sits underneath all of this, the one that tonight makes uncomfortably concrete. The gap between what we can track and what we can actually measure is not a theoretical vulnerability, it is a live one. 2026 EG1 just demonstrated it in real time, in the public record, with a blank field that anyone can look up right now. What happens when we take that same scenario and change just one variable, the size, turns out to require understanding a moment in 2022 when humanity did something it had never done before in the entire history of its existence on this planet. Part 11. The asteroid we actually moved. On September 26, 2022, a spacecraft travelling at approximately 6.1 kilometers per second slammed deliberately into an asteroid, and the history of this planet's relationship with the solar system changed in a way that is still not fully appreciated by most of the people living on it. The spacecraft was called DART, Double Asteroid Redirection Test. The name is straightforward to the point of being almost anticlimactic for what the mission actually accomplished. DART was a kinetic impactor, essentially a very expensive, very precisely aimed projectile. No explosive payload, no exotic propulsion. Just mass, velocity, and the physics of momentum transfer applied to a rock in space. The engineering elegance of it is that the concept requires nothing that does not already exist. You build a spacecraft, you aim it, you let orbital mechanics do the rest. The target was Dimorphos, a moonlet approximately 160 meters in diameter, orbiting a larger asteroid called Didymos, 160 meters, just above the potentially hazardous threshold. Large enough that an impact with Earth would produce regional devastation on a scale that would redefine the word disaster for anyone within several hundred kilometers of the impact site. The choice of Dimorphos as a target was not arbitrary. It was specifically selected because it sits in a binary system, and that binary geometry turned the deflection test into something measurable with extraordinary precision. Here is why that matters. If you hit a single isolated asteroid with a spacecraft and want to know whether you changed its orbit, you need to track its position over months or years and compare the new trajectory against the predicted one. The measurement is real but slow and subject to accumulating uncertainty. With a binary system, you have a built-in clock. Dimorphos orbits Didymos on a regular measurable period. If the impact changes Dimorphos's velocity even slightly, that change shows up immediately as a shift in the orbital period, a clock that runs faster or slower depending on how much momentum was transferred. The binary system converted a subtle trajectory change into a timing measurement that ground-based telescopes could detect within days of the impact. Before the impact, Dimorphos orbited Didymos once every 11 hours 55 minutes. After the impact, the orbital period was 11 hours 23 minutes. The change was 32 minutes, roughly 10 times larger than the minimum detectable change that scientists had established as the threshold for mission success. 10 times larger. The DART mission did not just demonstrate that a kinetic impactor could redirect an asteroid. It demonstrated that the redirect was significantly more effective than the most optimistic pre-impact models had predicted, and considerably more effective than the conservative baseline models that the mission had been designed around. The reason for that extra efficiency is a phenomenon called the ejector plume, and understanding it changes how you think about deflection physics going forward. When the DART spacecraft struck Dimorphos at 6.1 kilometers per second, it did not simply transfer its own momentum to the asteroid and stop. The impact excavated a crater, ejecting a large quantity of material from Dimorphos's surface in a cone-shaped plume extending away from the impact point. Observations from the Lysia Cube CubeSat that had been deployed from DART before impact, combined with ground-based and space-based telescope observations, showed a plume of debris extending thousands of kilometers from the impact site. Dust, gravel, boulders, a tail of material that persisted for weeks and was visible to telescopes across the solar system. When that ejected material left Dimorphos moving in the direction opposite to the spacecraft's incoming velocity, it acted as an additional propulsive force. Think of it as a rocket engine that the impact accidentally ignited. The spacecraft's momentum was one input. The ejected material's momentum was a second, larger input in the same direction. The combination produced a total momentum transfer far exceeding what the spacecraft's mass and velocity alone would have provided. The asteroid's own material became a contributor to its deflection. This is not a minor technical footnote. It fundamentally changes the calculation for how large a spacecraft you need, or how far in advance you need to launch it, to deflect a given asteroid by a given amount. If ejector enhancement is a reliable feature of kinetic impacts, and the DART result strongly suggests it is, though the magnitude will vary depending on the target's composition and structure, then the deflection toolkit is considerably more powerful than the pre-DART consensus assumed. The Planetary defense toolkit is not empty. That bears repeating because the rest of this story involves a great deal of what is missing, and what is not yet built, and what is still waiting for funding. Before getting to all of that, it is worth sitting with what DART actually proved. A real spacecraft built with existing technology, launched on a realistic budget, hit a real asteroid travelling through space and measurably, verifiably changed its orbit. The concept works, the physics work, the engineering works. Humanity has, exactly once in its entire history, intentionally altered the trajectory of a solar system body. That happened on September the 26th, 2022, and it worked better than anyone had officially predicted. Now, the critical constraint: sufficient warning time. Those three words carry the entire weight of the planetary defense problem, because DART proved the tool but did not change the fundamental requirement for using it. A kinetic impactor mission requires years of warning, ideally decades, to be effective. The physics of orbital mechanics are not negotiable on this point. A deflection works by applying a small velocity change to an asteroid when it is still far from Earth, then allowing that small change to accumulate into a large positional difference over the years or decades of remaining travel time before the predicted impact date. A nudge applied 10 years before impact can move an asteroid by millions of kilometers by the time it reaches Earth's vicinity. The same nudge applied 1 year before impact moves it by far less. Applied 1 week before impact, it is almost certainly insufficient to matter. The hierarchy of responses scales precisely with warning time, and it is worth laying out clearly because it is the framework within which everything else in tonight's story sits. With decades of warning, a kinetic impactor is the preferred option, tested, proven, deployable with existing technology. With years of warning, a kinetic impactor is still viable, but the mission planning becomes more urgent and the margin for error shrinks. With months of warning, more energetic options come into consideration, including multiple impactors or approaches that generate larger momentum transfers. With weeks of warning, the options narrow sharply, and evacuation of the predicted impact zone becomes a parallel track alongside any deflection attempt. With days of warning, deflection is off the table. The only remaining option is civil defense, moving people away from where the object is predicted to hit, if you have enough confidence in the impact prediction to know where that is. With hours or less, there is nothing to be done at the civilization level. Individual survival becomes a matter of geography and luck. Other deflection concepts exist and are worth understanding, even if they have not been tested at the scale DART was. The gravity tractor concept involves a spacecraft hovering near an asteroid, not touching it, just existing nearby, and using the mutual gravitational attraction between the spacecraft and the asteroid to slowly, patiently, tug the asteroid off its original course over years. The force is tiny, the timescale is long, but for an asteroid discovered with sufficient advance warning, the cumulative effect over years of continuous operation could produce a meaningful trajectory change without the complications of a physical impact. It is, in concept, the most elegant deflection method. No crash, no ejector uncertainty, just quiet gravitational persuasion applied over time. The Yarkovsky effect offers another subtle handle. Asteroids absorb sunlight on one side and radiate heat as they rotate, and the asymmetric thermal emission produces a tiny but continuous force that, over years, measurably shifts an asteroid's orbit. If you could change the surface reflectivity of an asteroid by painting it, coating it with reflective material, or even just landing enough material on its surface to alter the albedo, you could change the magnitude and direction of the Yarkovsky force, nudging the orbit onto a different long-term path. Again, the timescale is long and the warning time requirement is significant. But for a known threat with decades of lead time, it represents a real option. Nuclear deflection sits at the end of the option list, discussed carefully in the planetary defense literature not because anyone wants to use it, but because the physics demand that it remain on the table. For a very large object, several hundred meters or larger, or for a scenario where warning time is short and a kinetic impactor cannot transfer sufficient momentum, the energy output of a nuclear device standoff detonation may be the only tool capable of producing the required deflection. The DART mission does not make nuclear options obsolete. It makes them less likely to be needed, because it proved that kinetic impactors work better than expected. But the nuclear option remains part of the honest planetary defense planning conversation. An asteroid discovered 3 days before closest approach cannot be redirected by any method currently in existence. The DART spacecraft took 10 months to reach its target. The intervention window for a late discovered object simply does not exist. Tonight's flyby of 2026 EG1, discovered days ago with a blank diameter field, exists at exactly that end of the spectrum, where the toolkit that humanity has built and tested is irrelevant. because the warning time required to open that toolkit never arrived. The tool works. The detection system that would provide the warning time to use the tool is still catching up, and that gap between a proven deflection capability and an incomplete early warning architecture is the central unresolved tension in planetary defense right now, tonight, as this asteroid finishes its silent pass between Earth and the Moon. Part 12, the asteroid that almost had a 3% impact chance. In late 2024, a newly discovered asteroid entered the public asteroid risk tables and began climbing, and for several months it sat in the catalogue like a quiet alarm that most of the world did not know was ringing. The asteroid was designated 2024 YR4. It was found through routine survey operations, the same automated pipeline that finds hundreds of new near-Earth objects every year, flagging moving points of light against the fixed background of stars and submitting them for orbital calculation. In the early hours and days after discovery, every new asteroid goes through the same process. Preliminary observations come in. Software fits a trial orbit to the available data. The orbit is propagated forward in time to check for potential intersections with Earth's path. Most objects go through this process and come out the other side with impact probabilities that round to zero before the first news cycle ends. 2024 YR4 did not do that. Initial orbital calculations based on early observations with a limited arc length, meaning the asteroid had only been watched across a short stretch of sky over a short period of time, produced an impact probability that was, for the planetary defense community, genuinely alarming. The numbers climbed as more observations came in and the orbital solution developed. At one point during the observational arc development, the estimated probability of a collision with Earth reached approximately 3%, 1 in 33. Those odds do not sound catastrophic in isolation. If someone told you there was a 3% chance of rain tomorrow, you would probably leave the umbrella at home. But in the context of asteroid impact risk assessment, 3% is an extraordinary number, a number that exists in a category almost entirely by itself in the modern catalogue of tracked objects. To understand why 3% matters so much in this specific context, you need to understand how the risk tables normally look. The threshold that triggers formal planetary defense response planning, the point at which agencies begin activating protocols, scheduling emergency observation time, and briefing relevant officials, is considered to be in fractions of a percent. Fractions. An object at 0.1% draws serious attention. An object at 1% produces urgent follow-up campaigns across multiple continents. An object sitting at 3% sustained across multiple observation updates rather than appearing briefly as an artifact of sparse data and then collapsing to zero, was an event that the planetary defense community had essentially never encountered at that level in the era of modern systematic surveys. Every relevant observatory on the planet pointed at it. Observation time that is normally allocated months in advance through competitive proposal processes was redirected on short notice. Amateur astronomers with sufficiently capable equipment joined the follow-up campaign. The global network of near-Earth object observers, which normally functions as a distributed and somewhat loosely coordinated system, temporarily reorganized itself around a single target. The coordination was impressive. The urgency was real. The weeks that followed were a demonstration of how asteroid impact probability actually evolves in real time, and it is worth understanding this process in some detail because it is the same process, running in a much more compressed and less successful form, that applies to every close approach asteroid discovered late, including the ones passing Earth this week. Each new set of observations extended the known orbital arc. A longer arc means more data points constraining the orbital solution, which means the software has more information to work with when fitting a trajectory to the observations. A more constrained orbital solution produces tighter uncertainty bounds on the predicted trajectory. And tighter uncertainty bounds mean a smaller uncertainty ellipse, the region of space within which the asteroid's actual position at any future date might plausibly lie, given the current state of knowledge. Picture the uncertainty ellipse as a blurry region around the asteroid's predicted future path. At discovery, with only a few observations across a short arc, that blurry region is large, sometimes large enough to encompass a significant fraction of the inner solar system. As observations accumulate and the arc grows, the blurry region shrinks. It becomes a smaller and smaller cloud of possibility around a more and more precisely known trajectory. And as it shrinks, its relationship to Earth's position on the predicted encounter date changes. Sometimes the shrinking ellipse moves away from Earth entirely, and the impact probability collapses to 0. Sometimes, in the unsettling early phase of a new discovery, the ellipse actually appears to grow toward Earth before it begins to shrink away, an artifact of the orbital solution stabilizing around a geometry that temporarily highlights Earth-crossing possibilities before additional data resolves them. For 2024 YR4, the ellipse stayed uncomfortably close to Earth's predicted position for longer than the community would have preferred. The probability fluctuated as new observations came in, dipping slightly, rising again, refusing to collapse cleanly to 0 the way most objects do within their first few days of observation. For a period of months, the asteroid remained on the risk table at elevated probability, a persistent entry in the catalogue that represented a genuine, unresolved question about whether something catastrophic was going to happen on a specific future date. Then the James Webb Space Telescope was pointed at it. JWST is not, in its primary mission design, an asteroid characterization instrument. It is a general-purpose space observatory designed for cosmology, exoplanet atmospheres, galaxy formation, and a range of other astrophysical science programs that represent decades of community planning and proposal writing. Its observation schedule is managed through a competitive allocation process. Time on JWST is among the most precious commodities in contemporary astronomy. 2024 YR4's probability numbers were high enough to justify the extraordinary step of redirecting some of that precious time toward a solar system rock. JWST observed the asteroid in infrared wavelengths, producing two categories of data that the ground-based follow-up campaign could not provide on its own. The first was better astrometric position data, more precise measurements of the asteroid's location against the background sky, from a platform in space that does not suffer from the atmospheric distortion that limits ground-based positional accuracy. The second was the first meaningful infrared flux measurements of the object, actual thermal emission data that, combined with the infrared calibration models developed for asteroid characterization, allowed a much more constrained size estimate than optical observations alone could provide. The size information mattered for the probability calculation in a subtle but important way. Knowing the asteroid's physical size more precisely constrains certain parameters in the orbital model that are otherwise uncertain. The Yarkovsky effect, that tiny thermal force that gradually shifts asteroid orbits over time, depends on the asteroid's size, rotation, and thermal properties. With better size constraints from JWST's infrared data, the orbital propagation model could account for Yarkovsky perturbations more accurately, which tightened the uncertainty ellipse further. The combination of extended observational arc and infrared characterization data allowed orbit refinement to proceed to the point where the uncertainty ellipse no longer intersected Earth's position on the predicted encounter date. The impact probability dropped to effectively 0. 2024 YR4 was removed from the risk table. The months of elevated probability, the global observation campaign, the JWST time allocation, the briefings and the planning, and the quiet institutional anxiety, all of it resolved not through any physical intervention, but through the accumulation of better data. The system worked. That is the honest, accurate, important first conclusion from the 2024 YR4 episode. The global network of observatories functioned as intended. The follow-up protocols activated appropriately. JWST was deployed as an emergency characterization asset when the probability numbers justified it. An object that briefly sat at 3% impact probability was tracked, measured, and resolved without any intervention beyond observation. The planetary defense community handled it correctly, and the outcome was the right one. The second conclusion is less comfortable. The resolution took months. During those months, the uncertainty lived in the public record, visible to anyone who checked the risk tables, generating coverage ranging from careful science journalism to outright catastrophism, producing a period of genuine public anxiety about an event that ultimately did not materialize. The infrastructure required to resolve the uncertainty in infrared, an instrument as powerful and expensive and oversubscribed as JWST, is not normally available for asteroid characterization. It was deployed in this case because 3% is a number that cannot be ignored. For an object at 0.05%, the JWST allocation would not have been approved. For an object at 0.001%, well within the range that still represents meaningful risk at sufficient size, the characterization resources required to resolve the uncertainty simply would not be mobilized, and for an object discovered 3 days before its closest approach, with no time to develop an observational arc and no available radar or infrared observation windows in the relevant timeframe, the entire resolution process that saved the 2024 YR4 scenario cannot run at all. The arc development takes weeks at minimum. The JWST allocation process takes time that does not exist. The orbital solution that would shrink the uncertainty ellipse away from Earth's position requires observations that have not yet occurred and cannot occur before the encounter is over. The outcome of that compressed scenario is what the catalogue shows tonight. Blank fields, an asteroid that has passed or is passing right now, its physical nature still unknown, its size still unconfirmed, the question of what it actually was left open because the timeline between discovery and closest approach was simply too short for the characterization system to engage. The future of changing that timeline, of catching these objects earlier, characterizing them faster, and building the detection infrastructure that gives planetary defense the lead time it actually needs, is under construction right now, and it is coming from a direction that will transform not just asteroid science, but our understanding of the entire solar system. Part 13. The observatory about to transform asteroid discovery. Perched on a mountain in northern Chile, at an altitude of 2,800 meters above sea level, where the atmosphere is thin and the seeing conditions are among the best on the surface of this planet, a telescope unlike any previously built for wide-field astronomy is preparing to begin its primary survey operations, and the asteroid catalogue will never look the same afterward. The Vera C. Rubin Observatory carries a name worth understanding before we discuss what the instrument itself will do. Vera Rubin was an American astronomer who spent decades making careful, meticulous observations of how galaxies rotate, measuring the orbital velocities of stars at different distances from galactic centers, and comparing those measurements against what Newtonian gravity predicted. What she found was a persistent, reproducible discrepancy. Galaxies were rotating as if they contained far more mass than the visible stars and gas could account for. The outer regions of galaxies were moving too fast. The mathematics of gravity said they should be flying apart, but they were not. Something was holding them together, something massive, something distributed throughout and around galaxies in enormous invisible halos, something that did not emit or reflect light in any wavelength that existing instruments could detect. Rubin did not name this phenomenon. The term dark matter had been used by others before her, but her observational work across dozens of galaxies, conducted with a rigor and consistency that made the results impossible to dismiss, turned dark matter from a theoretical curiosity into an observational reality that the astronomical community could no longer avoid confronting. She did this work largely without the recognition her male contemporaries received for comparable contributions, which is a separate story that astronomy has spent the subsequent decades slowly and inadequately reckoning with. The decision to name this observatory after her is, among other things, an acknowledgement of a debt. The observatory name for her is designed to conduct something called the Legacy Survey of Space and Time. The name is intentionally enormous, and the ambition matches it in every particular. Over a planned operational period of 10 years, the Rubin Observatory will image the entire accessible southern sky, everything visible from its Chilean mountaintop, repeatedly, systematically, on a cadence that returns to every patch of sky roughly every 3 to 4 nights. The resulting dataset will be the largest standardized astronomical survey ever assembled, a decade-long record of everything that moves, brightens, dims, appears or disappears across billions of objects simultaneously. The camera at the heart of the Rubin telescope is the largest digital camera ever constructed for astronomical purposes, and the numbers involved require a moment to sit with. 3,200,000,000 pixels. A single exposure covers a field of view large enough to contain approximately 45 full moons side by side. The telescope's primary mirror is 8.4 meters in diameter, large enough to collect light from objects billions of times fainter than anything visible to the naked eye. The combination of aperture size, field of view, and survey cadence produces a system that operates at a scale qualitatively different from anything that has come before it in ground-based optical astronomy. For asteroid detection specifically, the operational cadence is what makes Rubin transformative rather than merely impressive. Detection of moving objects in astronomy requires comparison. You need at least 2 images of the same patch of sky, separated in time, to identify a source that has shifted position against the fixed background of stars. Current discovery surveys do this well, but they are constrained by the size of their camera fields, the aperture of their telescopes, and the scheduling pressures of competing science programs. Rubin's wide field means it covers more sky per exposure than any current survey instrument. Its large aperture means it detects fainter objects at any given distance. And its systematic cadence means every patch of accessible sky gets revisited on a schedule regular enough to catch objects moving at the angular rates typical of near-Earth asteroids at moderate distances. Projections from the planetary defense community suggest that Rubin will discover millions of previously unknown solar system objects within its first few years of full operation. Not hundreds, not thousands, millions. Asteroids, comets, trans-Neptunian objects in the outer solar system, Jupiter Trojans, main belt asteroids that current surveys have not yet catalogued. The full population of small solar system bodies accessible from Chile's southern sky will be mapped at a level of completeness that current catalogues cannot approach. The specifically relevant capability for planetary defense is Rubin's sensitivity to faint, fast-moving objects at moderate distances. This is the size class that tonight's story is actually about. The Chelyabinsk meteor was approximately 20 meters wide. The Tunguska impactor was 50 to 100 meters. These objects, the sub-100 meter near-Earth asteroids that represent the most common category of potentially damaging impactors, are largely uncatalogued in current surveys because they are simply too faint to detect until they are uncomfortably close. Current surveys find them when they are nearby, which means the discovery to closest approach timeline is measured in days rather than years. The characterization pipeline cannot engage. The diameter fields stay blank. The encounter happens before any useful physical measurement can be made. Rubin changes this equation by detecting fainter objects at greater distances. An asteroid that current surveys cannot see until it is close enough to be 2 or 3 days from closest approach should, in many cases, be detectable by Rubin when it's still months or years away. That additional lead time is not a minor improvement. It is the difference between a blank catalogue entry and a characterized object with a known size, a constrained orbit, and a follow-up observation history. It is the difference between an encounter that planetary defense can assess in advance and one that the catalogue records in retrospect. Rubin will not solve every detection problem. It is important to be clear about this, because the temptation when describing a genuinely impressive new instrument is to overstate its reach. Rubin is a ground-based optical telescope. It cannot observe into the solar glare any more than any other ground-based instrument can. The sunward blind spot, the geometric vulnerability that allowed the Chelyabinsk meteor to arrive undetected and that remains the central architectural weakness of ground-based planetary defense, is not addressed by Rubin. Objects approaching from the sun's direction will remain invisible to it for the same reasons they are invisible to every other optical telescope operating from Earth's surface. For the vast majority of the accessible sky, everything that is not in the sun's immediate vicinity, Rubin represents a step-change improvement in detection completeness and lead time. For the specific category of sunward approach objects, the problem remains exactly as it was, and the solution remains exactly what it has been: a space-based infrared observatory in solar orbit, which is to say NEO surveyor, which is to say the mission that is still waiting in the development queue for stable funding. Rubin and NEO surveyor are complementary systems, not competing ones. Together they would cover the detection landscape far more completely than either can alone. Separately, each addresses a different portion of the overall gap. The asteroid catalogue that exists today will look sparse and incomplete by comparison to what Rubin will produce within a decade of full operations. This is not speculation. The models are clear, and they are based on Rubin's known instrumental capabilities applied to the estimated actual population of solar system small bodies. The catalogue is going to grow by orders of magnitude. Objects that are currently unknown will become known. Orbits that are currently unconstrained will be determined. The inventory of potential impactors that planetary defense must track will expand enormously. And this creates a challenge that is worth naming directly, because it is not the kind of problem that sounds like a problem until you think about it carefully. What do you do when you suddenly know about millions of additional objects and need to characterize them, follow them up, separate the genuinely concerning from the vast background of harmless rock, and maintain continuous surveillance on the subset of the new catalogue that represents meaningful impact risk. The follow-up demand that Rubin will generate is expected to exceed the current capacity of the global follow-up observation network by a substantial margin. Every newly discovered near-Earth object requires additional observations to refine its orbit. Every object with an impact probability above a certain threshold requires physical characterization observations. Every object that develops an elevated risk profile requires the kind of intensive multi-observatory campaign that 2024 YR4 received. Rubin will produce these objects at a rate that current infrastructure cannot service without significant expansion. The characterization backlog that exists today, where thousands of known near-Earth objects lack meaningful physical data, will not be solved by Rubin discovering millions more objects. It will be complicated by it, unless the follow-up infrastructure, the radar facilities, the infrared observing time, the spectroscopic resources, expands in parallel with the discovery rate. The catalogue is going to grow faster than the characterization pipeline can currently run. That gap, already present tonight in the blank diameter fields of this week's close approach objects, will widen before it narrows unless deliberate investment closes it. The scale of data that Rubin will generate, millions of images, billions of source measurements, petabytes of information per year, also represents a processing challenge that reframes the entire question of how asteroid science gets done. The human astronomical community that currently reviews, follows up, and interprets near-Earth object detections is not going to scale to the volume of candidates that Rubin produces. The math does not work. The number of candidates will exceed the human capacity to evaluate them individually by orders of magnitude, which means the future of planetary defense in the Rubin era is not just a question of better telescopes and more observation time. It is a question of who, or more precisely what, is going to be doing the watching. Part 14. The AI systems now hunting asteroids. Modern sky surveys do not produce data that any human team could process manually. They produce floods, not metaphorical floods. Actual, literal, overwhelming volumes of digital information generated every clear night by telescopes that never sleep, never take breaks, and never get tired of staring at the same patch of sky for the fourth consecutive hour. The Catalina Sky Survey, operating from mountaintops in Arizona, generates tens of thousands of images on a productive night. The Pan-STARRS system in Hawaii, the Panoramic Survey Telescope and Rapid Response System, runs 2 telescopes simultaneously and produces image data at a rate that fills hard drives faster than most institutions can archive it. The Atlas Network, the Asteroid Terrestrial Impact Last Alert System, operates 4 telescopes across Hawaii, Chile and South Africa specifically designed to catch fast-moving objects on short timescales, scanning the entire accessible sky multiple times per night. Each of these systems produces images containing hundreds of thousands of individual detected sources per frame. Stars, galaxies, satellite trails, cosmic ray hits on the detector, optical artifacts from bright star reflections, atmospheric distortion events, and somewhere buried in all of it, on any given night, moving points of light that represent previously unknown near-Earth objects. Finding those moving points requires comparing images of the same patch of sky taken at different times, typically separated by 15 minutes to an hour, and identifying sources that have shifted position against the fixed background of stars. Then it requires rejecting everything that is not a real moving solar system object, the cosmic rays that appear in one image and not another, the satellite trails that streak across frames at the wrong angular rate, the hot pixels that behave like point sources, the optical ghosts that haunt the edges of bright star images, the atmospheric scintillation events that make a fixed star appear to jump between exposures. In the early years of systematic asteroid surveys in the 1990s and early 2000s, this filtering process required substantial human involvement. Teams of astronomers, often including graduate students performing what the field euphemistically called service observing, would sit at computer terminals and visually inspect candidate detections one by one. They would look at small image cutouts centered on each candidate, a few dozen pixels across, showing a faint point of light in its immediate surroundings, and apply their trained judgment to decide whether what they were looking at was a real moving object or a noise artifact. The process was called blinking, flipping rapidly between 2 images of the same field to see whether anything moved. It worked. It produced real discoveries. The systematic surveys of that era found thousands of near-Earth objects that had never been catalogued before. including many of the largest and most potentially dangerous ones. The Spacewatch program, Linear, Neat, Lonios. These surveys collectively transformed the near-Earth object catalogue from a sparse collection of accidentally discovered rocks into a systematic inventory with real completeness at the larger size ranges. The human blinkers who sat in front of those terminals night after night contributed to one of the more quietly consequential scientific efforts of the late 20th century. But it did not scale. The discovery rate was fundamentally limited by the amount of human attention available, and human attention is finite, expensive, and subject to fatigue in ways that matter when you're looking for faint, fast-moving objects in noisy image data at 2 a.m. after 6 consecutive hours of the same task. As survey systems improved, larger cameras, faster readout electronics, better telescope mounts, more automated operations, the data rate increased faster than the human workforce reviewing it. The bottleneck shifted from the telescopes to the people. More sky could be surveyed than could be humanly processed. Machine learning systems changed that equation, and changed it in a way that was not immediately obvious it would work as well as it did. The core challenge for an automated detection system is distinguishing real moving objects from the enormous variety of image artifacts that mimic them. A cosmic ray hit on a detector produces a bright point source in one image that is absent in the next, exactly the signature of a real object detected once and then moved out of frame, except that cosmic rays appear in random positions and real asteroids follow predictable motion vectors. Satellite trails streak across images at rates and angles determined by orbital mechanics, and the trail endpoints can sometimes resemble point sources in certain detection algorithms. Hot pixels on aging detectors produce persistent false sources that appear consistently across multiple images of the same field. Optical ghosts, reflections of bright stars bouncing between lens elements in the optical path, appear at predictable offsets from their parent stars and need to be recognized as artifacts rather than independent sources. Human astronomers learn to recognize all of these artifacts through experience. After reviewing enough images, the visual pattern of a cosmic ray hit becomes distinctive. The appearance of a satellite trail becomes immediately identifiable. The characteristic behavior of a hot pixel becomes obvious. The trained human brain applies this pattern recognition rapidly and largely unconsciously. The challenge was translating that learned pattern recognition into a form that a computer could replicate. Convolutional neural networks turned out to be the right tool for this translation. A convolutional neural network processes image data by applying learned filters at multiple spatial scales, extracting features that correspond to the visual patterns the network has been trained to recognize. Trained on large datasets of confirmed asteroid detections, real moving objects with verified follow-up observations, alongside confirmed false positives of every type that regularly appears in survey data, these networks learn to distinguish between them with accuracy that matches and in some cases exceeds expert human performance. Not approximately matches. Matches in controlled comparisons where the same candidate datasets were evaluated by both trained astronomers and the neural network classifier, with the network's performance measured against the human consensus. The speed advantage is not comparable. It is not that AI systems are somewhat faster than human reviewers. It is that a neural network can evaluate tens of thousands of candidate detections in the time it would take a human astronomer to carefully examine a few hundred. The entire nightly candidate list from a major survey, candidates that would have required a team of reviewers working through the night in earlier decades, can be processed, classified, and prioritized in minutes. Real candidates are flagged for follow-up observation before the night is even over. False positives are rejected without consuming any human attention. Beyond the basic real or artifact classification, machine learning systems are now being applied to more sophisticated aspects of the asteroid detection pipeline. Tracklet linking, the process of connecting individual detections of the same object across multiple images taken on the same night, and then connecting those nightly tracklets across multiple nights to build an orbital arc, is a combinatorially complex problem that scales badly with the number of detections. As the detection rate increases, the number of possible linkages to consider grows faster than linearly, quickly reaching volumes that make exhaustive search computationally impractical. Machine learning approaches to tracklet linking use the physical constraints of orbital mechanics to prune the search space, identifying the combinations of detections that are consistent with real, solar system trajectories and rejecting the vast majority that are not. Anomaly detection represents another frontier. Standard asteroid detection pipelines are optimized to find objects that behave like known asteroids, moving at rates and along trajectories consistent with solar system orbital dynamics. Objects that behave unusually, moving at unexpected rates, showing non-gravitational accelerations from outgassing activity, displaying brightness variations inconsistent with simple rotation, can fall outside the parameter space that standard pipelines are tuned to catch. Machine learning anomaly detection systems, trained on the full distribution of known object behaviors, can flag detections that deviate from expected patterns, potentially catching unusual objects, active asteroids, cometary bodies on unusual orbits, or in the most extreme cases, objects with truly unexpected characteristics that rule-based pipelines might miss or misclassify. The integration of these AI systems into discovery pipelines has already measurably increased the rate at which new near-Earth objects are found and reported. The improvement is not marginal. Survey systems that integrated machine learning classifiers saw their effective detection rates increase, because the reduction in false positive rates meant that genuine candidates were more reliably elevated for follow-up rather than being buried in noise. The signal-to-noise ratio of the entire pipeline improved, not just the processing speed. When the Rubin Observatory reaches full operational status and begins generating data volumes orders of magnitude larger than current surveys, we are talking about 15 terabytes of raw image data per night. Every night for 10 years, automated AI processing will not be an enhancement to the discovery pipeline. It will be the only way the pipeline can function at all. There is no version of the Rubin era in which human astronomers manually review the nightly candidate list. The numbers make that impossible by such a large margin that the question barely deserves to be framed as a trade-off. Human astronomers in the Rubin era will set scientific priorities, investigate flagged anomalies, design targeted follow-up programs, interpret unusual results, and make the judgment calls that require contextual scientific understanding. The initial triage of the nightly data torrent, the identification and classification of moving object candidates from billions of individual measurements, will be the domain of algorithms running automatically, continuously, faster than any human team could replicate. There is something genuinely appropriate about this architecture when you think about what planetary defense is actually trying to accomplish. The asteroid threat is fundamentally a statistics problem embedded in an observation problem. Among the hundreds of thousands of tracked objects in the current catalogue and the millions that will be added by Rubin, a tiny fraction at any given time represent meaningful collision probabilities. Identifying that fraction efficiently, without missing the genuinely dangerous objects that could be hiding in the noise, and without overwhelming the follow-up system with false alarms that consume resources needed for real threats, is precisely the kind of high-dimensional pattern recognition problem that machine learning was developed to solve. 2026 EG-1, discovered days ago, its diameter fields blank, its physical nature unknown as it crosses inside the Moon's orbital distance tonight, exists at a specific moment in the development of this system. The detection pipeline found it. The orbital calculation worked. The characterization pipeline did not have time to engage. The AI systems that will eventually close that gap are running, improving, being trained on larger data sets with better labels and more sophisticated architectures. The Rubin Observatory that will generate the data those systems need to operate at full effectiveness is on a mountain in Chile, preparing to open its eyes on the southern sky. The question of whether that timeline is fast enough is not an abstract one. Tonight illustrated in the live catalogue data exactly what the current gap looks like from the inside. The next question is the oldest one in this entire story, and the one that everything else has been building toward. Part 15. The real meaning of tonight's flyby. At 0327 Coordinated Universal Time on March 13, 2026, Asteroid 2026 EG-1 passed 318,000 kilometers from Earth, and the vast majority of the 8 billion people living on this planet had absolutely no idea it was happening. They were asleep, or working night shifts, or scrolling through social media feeds algorithmically optimized to show them everything except the quiet astronomical event occurring between them and the Moon. Some of them were watching this video, most were not. The asteroid did not announce itself. It produced no light show, no detectable vibration, no signal of any kind that an unequipped human observer could perceive. It was a rock in space, following a trajectory determined by the same gravitational mathematics that keeps the planets in their orbits, passing through a region of space that happens to be inside the Moon's orbital distance from Earth, and then continuing outward, decelerating relative to Earth as it climbed away from the Sun's gravity well, beginning the long arc that will eventually bring it back around for another orbit, and, at some future date that the orbital mechanics can already calculate, another close approach. You're watching this either in the minutes before that moment or in the hours after it. Either way, the asteroid has passed or will pass without incident. It will continue along its orbital path, looping around the Sun, catalogued now in a way it was not a week ago, its trajectory filed in the permanent record of known near-Earth objects, its physical nature still stubbornly, completely unknown. No damage, no impact, no emergency. From a purely practical standpoint, tonight was a non-event, and if you came here expecting otherwise, the universe has once again declined to perform on schedule. But let us be honest about what tonight actually demonstrated, because that honesty is the entire point of having spent this much time with a rock that did nothing dramatic. The temptation after a non-event is to treat it as a non-story, to file it away in the mental category of things that were briefly concerning and then turned out to be fine. Tonight does not belong in that category. Tonight belongs in a different one. Things that were fine and revealed something important about the conditions under which they might not be. The discovery came late. Days before closest approach, 2026 EG1 entered the catalogue as a newly identified near-Earth object. The orbit was determined quickly and accurately, and that speed of orbital determination is worth genuine appreciation. The global network of observatories, the automated processing pipelines, the follow-up protocols that kick in when a new object is flagged, they worked. The trajectory was pinned down, the close approach distance was calculated, the miss was confirmed. That part of the system performed exactly as designed, and it performed well. The physical characterization never happened. Not because anyone failed, not because a protocol was skipped, not because the right people were not paying attention. It never happened because the system as currently designed and funded does not have the infrastructure to characterize every newly discovered small asteroid before its first close approach. The characterization pipeline runs behind the discovery pipeline as a structural feature of how planetary defense is currently resourced. For objects discovered with months of lead time, the gap can sometimes be closed, follow-up observations scheduled, radar time requested, infrared measurements obtained. For objects found days before closest approach, the gap cannot be closed. The timeline does not allow it. The blank data fields are not an accident or an oversight. They are the predictable, documented output of a system operating at the limits of its current capability. The size of 2026 EG1 remains unknown tonight. It will likely remain unknown for some time, possibly indefinitely, because once an asteroid has made its close approach and moved away from Earth, the urgency for follow-up characterization drops sharply. Resources get redirected to the next newly discovered object, the next elevated probability entry in the risk tables, the next thing that demands immediate attention. The catalogue entry for 2026 EG1 will persist with its blank diameter field until someone specifically prioritizes filling it, and in a world of limited observation time and growing catalogues, that prioritization may never arrive. Statistically, the object was almost certainly small. The size distribution of near-Earth asteroids is heavily weighted towards smaller objects. The population of rocks under 20 meters vastly outnumbers the population of rocks over 100 meters, which vastly outnumbers the population of rocks over 1 kilometer. A randomly selected newly discovered near-Earth asteroid is far more likely to be harmless than hazardous. This is a real and meaningful statistical fact, and it is the foundation of the reasonable confidence that tonight's flyby posed no threat. But here is the thing about statistical reasoning that makes it insufficient as a sole basis for planetary defense. Statistics describe populations. They do not describe individual objects. The size distribution tells you that most newly discovered near-Earth asteroids are small. It does not tell you that this specific newly discovered near-Earth asteroid is small. For that, you need a measurement. And the measurement does not exist. The detection and characterization gap that applied to 2026 EG1 tonight applies with identical force to a hypothetical object, with identical discovery circumstances and a diameter of 100 meters instead of 10. The blank data fields would look exactly the same. the discovery timeline would be identical, the lead time available for any response, which is to say, essentially no lead time at all, would be identical. The catalogue entry for the 100-metre object on the day of its discovery, and through the days leading to its closest approach, would be indistinguishable from the catalogue entry for the 10-metre object. You would not know which one you were dealing with until you had measurements that the current system cannot always produce in time. This is not a hypothetical designed to manufacture alarm. It is the structural reality of how the current detection and characterization architecture handles late discovered objects, and it is worth stating plainly rather than burying in qualifications. The sunward blind spot is real. Objects approaching from the direction of the sun cannot be detected by ground-based optical surveys until they have passed Earth or are extremely close to closest approach. The Chelyabinsk meteor demonstrated this in 2013. The geometry has not changed. The blind spot has not closed. Every day that NEO-Surveyor remains unlaunched is another day that the sunward approach corridor remains unmonitored by the kind of instrument capable of monitoring it effectively. The characterization backlog is real. Thousands of known near-Earth objects lack meaningful physical data. The backlog grows every year as discovery surveys find new objects faster than characterization resources can process them. Tonight added at least one more entry to that backlog, an object that made its closest approach to Earth with its diameter unknown and its albedo unmeasured. The underfunding of planetary defense relative to the scale of the risk it addresses is real and documented. The cost asymmetry between the missions that would close these gaps and the consequences of the gaps remaining open is not a matter of interpretation. It is arithmetic. The numbers are public. The case has been made repeatedly by scientists who understand the problem better than anyone. The resources required to address it exist within budgets that routinely spend comparable amounts on projects with far smaller expected returns. These are not talking points assembled to support a predetermined conclusion. They are features of the current system, visible in public databases, acknowledged in scientific literature, discussed openly in the planetary defense community. They are also addressable. That is the part that matters most, and the part that the alarm and the frustration and the late-night anxiety about blank diameter fields should ultimately point toward. Progress is real, and it deserves to be stated with the same directness as the gaps. DART worked, and it worked better than predicted, and it proved that humanity can physically alter the trajectory of a solar system body when given the time and the tools to do so. The Rubin Observatory is coming, and it will transform the near-Earth object catalogue in ways that will make the current inventory look like a rough sketch. AI detection pipelines are improving continuously, processing data faster and more accurately than human reviewers could manage at any comparable scale. The James Webb Space Telescope demonstrated with 2024 YR4 that space-based infrared capability can resolve impact probability uncertainties that ground-based observations alone cannot close. The scientific understanding of impact risk, deflection physics, detection architecture, and characterization methodology is more sophisticated and more quantitative than it has ever been in the history of this field. The community working on these problems is not complacent. It is not unaware of the gaps. It is not waiting for someone to notice. It is doing the work with the resources it has, making the case for the resources it needs, building the systems that will make the next decade of planetary defense substantially more capable than the current one. The people in this field are, by any reasonable measure, among the most consequential scientists on the planet, working on a problem whose stakes are literally civilizational, doing so largely without the public attention or the institutional priority that the problem's importance would seem to demand. What tonight looked like, in practice, was a small rock passing silently between Earth and the Moon, while most of the world slept, unaware of its existence. The database will be updated, the close approach will be logged. 2026 EG1 will take its place in the long catalogue of routine encounters, one entry among thousands, its blank diameter field a small and unremarkable data gap in an enormous and mostly well-characterized inventory. And the question that sits underneath all of this, the one that every blank field and every late discovery and every underfunded mission has been quietly pointing toward throughout this entire story, is the simplest one and the most important one, and the one that tonight has illustrated with a clarity that no amount of statistical reassurance can entirely dissolve. If the rock had been larger, approaching from the sunward blind spot discovered 3 days before closest approach, exactly the way this one was, the catalogue entry would look identical to what you can look up right now. The blank field where the diameter should be would look exactly the same. Look at that blank field, hold it in your mind for a moment. Think about what it represents, not just for this object, on this night, but for the architecture of the system that produced it and the gaps that system still contains, and tell me honestly that you are certain it will always be a small rock.